and also the solute, when we're dealing with vapor pressure of a pure substance, we're looking at the sort of the escape of that pure substance from its own liquid. And so you could imagine if you put that substance in another liquid, it's diluted. Its vapor pressure could be dramatically different because the solute is surrounded by some other molecule. And so there's no reason why you would expect it to behave like it would if it was surrounded by itself, its own kind, right? Its vapor pressure in itself is going to be governed by Raoult's law. But if you take that solute and stick it in some other environment, its vapor pressure, it might be the same coincidentally, in which case you'd have an ideal solution. But it could be dramatically lower if it likes the new environment, right? But it could be dramatically higher if it cannot stand the new environment. So acetone and carbon disulfide do not like each other, and so the acetone vapor pressure is much higher. But acetone and chloroform, it's much lower because acetone can hydrogen bond with chloroform and it can't hydrogen bond with itself. So those are situations where you have non-ideal solutions. But it's nice, I like to think of things from the molecular point of view. If we plot, instead of Henry's law and Raoult's law, those only deal with the extremes. What governs the middle? And how would we address the middle region? So we have what we call activities and activity coefficients. And so if you wanted to plot out experimentally this whole curve, you could collect your vapor pressure data, and then the deviation from ideal would be using this activity coefficient, this activity, not the partial pressure. So the activity could be arrived at by putting an activity coefficient in front of Raoult's law. So see, here's Raoult's law right here. XA times the vapor pressure of A, and that would give us PA. But we could put a coefficient in front of this and correct that term to give us the actual activity of that substance. And then if we wanted to look at that activity coefficient, notice it's a function of XA. We could rearrange this and we end up with this activity coefficient is the actual behavior divided by the mole fraction. And so these, at any one of these points, you could come up with the activity for acetone and the activity for carbon disulfide, and then you still use Dalton's law to take this number plus this number. So I'll do a plus, gives us that number, which is equals. So that plus that equals the top number. This is just an empirical result. So we're just getting those activities at each data point. So at a given mole fraction, you'll have a different activity coefficient and a different activity. Okay. It would really be nice to have an equation that gives us the shape of that line. And one of those equations is the Margulies equation, where we take the Raoult's law and we correct it with a term that's a function of the mole fraction. And so we've added in kind of this Gaussian-like term. It's a difference squared, so it's kind of like a Gaussian, and it's sitting on top of this slope here. So it's got a strange shape. It doesn't really look like a Gaussian. We've got this Raoult's law piece and this correction piece that gives us the activities. And this beta term depends upon those interactions, the energy of A plus B versus the energy of A and the energy of B.
Are those internal energies, or is that you?
Yeah, internal energies of those interactions. But I've looked for Margulies equations for these different things, and this beta term is hard to find. They end up with Wilson coefficient. I mean, if you want to know more about that and the rabbit hole that is, or more like the ant mound that is, read Nilan's thesis from my group a few years back. He went and he outlined all of those different equations. We were trying to find azeotropes. And he has a great thesis. He pulled the thread on all of these equations that are buried inside that beta. But anyway, you can get, if you change beta, if beta is 0, then you have e to the 0, which is 1, so you have Raoult's law. If beta is less than 0, you have attractive situations like acetone chloroform. If beta is much greater than 0, then you end up with these very non-ideal situations like carbon disulfide and acetone. But when you have this shape now, you could then model these activity curves with the Margulies equation, and you would get things like this. Okay. Now let's talk about this region between the liquid composition and the vapor composition. So we're still in a PX diagram, and here's where we're going to use all three, XA, YA, and ZA. Okay, so we haven't used ZA. Now, if you're in a pressure composition phase diagram, you're going to be in a sealed container, so you can actually control the pressure with a piston or what have you. And so let's think about the piston situation. PX phase diagrams are interesting in that, to me, they kind of go against intuition. I typically think of liquids as being in the bottom of a container and vapor being in the top of a container, right? And that's what you see when you see a beaker. The liquid's in the bottom and the gas is in the top. This is a phase diagram. It's not a container. Okay? High pressure is going to be liquid. Low pressure is going to be gas. Okay, so whenever you're looking at a phase diagram and you're trying to identify what zone is where, always look at the x-axis and the y-axis and figure out which region will be liquid, which region will be gas. And in a PX, listen carefully, a PX phase diagram, liquid's on top. Okay, we're about to switch to TX and liquid will be on bottom. Okay, so, but in this case, PX, liquid's on top. And so here now we have this right here, this dotted line. We have a new iso. Okay, so we have an isopleth. Sort of the root of that word plethora or amount. Yeah. So the same amount on that vertical line. So we're starting at A. We have a piston that's touching the liquid and we're lifting it up. And when we start to lift it up, we start to produce some vapor. Okay. Now we haven't changed the composition in the container, but we start out here. It's all liquid. Here it's mostly liquid, and we have this lever rule situation. So we have a little bit of vapor here, and we have mostly liquid. So we've got a big mass here of liquid and a little mass of vapor. And now we've pulled the piston out a little further, and now we have mostly vapor and a little bit of liquid. When we get past this line, it's all vapor.
Should those piston diagrams be BCD instead of ABC? Because A would be full liquid, right?
Yeah, A is full liquid.
So I guess it'd be BCD in this case. Like a little cartoon.
Oh, the cartoons? Oh, interesting. Let's see. Yeah, so let's make this one B. This one's C. I've never had anybody point that out to me. Thank you. And this is D. I think these might be from different books. So that's why they don't line up. Yeah. And so what's going on then is this isopleth, see overall composition Z, we have Z benzene here. And so that's the overall composition of benzene. And then this line right here, which letter would I use to label this line right there? X or Y, those are your two choices.
Oh,
Yeah, this is Y benzene. And then this line right here is X. Okay. A lot of times we just label the x-axis X benzene, but really it should be Z benzene. If we're showing the vapor and the liquid phases, then but it's typical to see X, like on our Kahoot we just had, it was X, across the bottom. But that was a liquid vapor, phase diagram. We just didn't have the vapor liquid lines both on there. We're really just plotting the vapor composition.
So on the horizontal C line,
Yes.
should we use the lever rule?
Okay, yes, and so there's a name for that horizontal line. That's called a tie line. Okay. Yeah, so these horizontal lines are TIE, so tie lines. So it ties both ends, both the vapor and the liquid. So it's just a tie line that ties them both together.
So the C portion would be, or where the little portion is on C would be the liquid, and the larger portion would be the vapor.
Just the reverse.
So the reverse of what I said, or
Yes, the reverse of what you said, because the vapor's at the bottom, and so the distance from C to that vapor line is the vapor composition, the amount of vapor you have, and the distance from C to the liquid line is the amount proportional to the amount of liquid you have. Let me show you this next picture. See, so we're zoomed in. This is the tie line, and this is the relationship. So what I just said might have been inversed. Yeah. So you have this distance here, which is LV.
Very correct.
Yeah, and this distance here is LL. LL. And the number of moles times LV is equal to the number of moles times LL. So this is a really big line, so that means this is going to be a small amount of vapor. And this is a really short line, so it's going to be a large amount of liquid. Because we got to balance the seesaw. And so if the length gets long, the mass gets small. And if the mass is big, the length is short. Yes?
Should that be NL is equal to ZA minus XA? And NV equal to YA minus...
Let's see, LL, the liquid, would be the difference between Z. So this is, this is ZA, and it's this value minus XA.
I'm saying that those are moles, and that's comparing the length.
Yeah, so we're getting the lengths. So these lengths here, ZA minus XA, is this L piece. And then N sub L is the number of moles of liquid you have.
But wouldn't it need to be in the same units though? So.
No, well, it's moles times length equals moles times length. So the units work out.
But I mean, for this part down the bottom, ZA minus XA,
Yes?
wouldn't that be in moles? So we need to do moles equal to mole. Something like NL is equal to...
Well, ZA and XA are unitless. They're moles per total mole.
Okay, so...
Yeah, so they're mole fractions. So they're actually unitless values.
Then the unitless value would be equal to a length. That's what kind of...
We're just length of that line. It's not a meter. It's just the length of that line on this diagram. Yeah. Yeah, so even though we're talking about length, it really doesn't have units of length. Yeah, it's just the length of that line drawn on this diagram. So it's whatever the x-axis units are, which are unitless because they're fractions. Yeah. So these L's, we call them lengths, but it's just because we're looking at this line and saying, how long is that line? We're not actually measuring in meters or anything like that. Yeah, so we're just saying, it's, yeah, so it's, and then this one is YA minus ZA, so this value over here is YA. So this distance would be YA minus ZA, that would give us LV, and ZA minus XA would give us LL, and we'd have the ratio of those moles being corresponding to that. And we will do an example of this with the partial mixability. So when we get to solutions, that's a more common situation than vapor-liquid equilibrium values. And so instead of doing a lever rule problem with this phase diagram, we will do one, but we'll do it with a two-phase liquid and try to figure out how many moles are in each phase. So we will get to the lever rule problems and just do it later. Okay, let's look at the TX phase diagram. But no, those were some great questions because, I look at it and I think, okay, this makes sense to me, but you guys are refreshing or learning it. You've got to ask questions so we know what we're going through.